Hi, everyone, and thank you for joining. My name is Ori Kam. My plan here in this talk is to show a new concept, a new API that we want to introduce to RTE flow, which basically will improve it even more. So let's start. So who am I? First of all, let's start with that. I'm a software engineer at NVIDIA, previously Mellanox. I have over 20 years of experience in programming in general and over 5 years experience with the DPDK community. I'm an RTE flow and regex maintainer, and my mail is orica@nvidia.com. Keep this mail in mind if you later want to contact me about this new approach that we plan to take. Okay, the agenda for today, sorry, is first to introduce a few words about RTE flow. I know all of you probably know it, but I want to say a few things about it. I'll show two types of different usage of RTE flow in two types of applications. Then I'll show the limitation that we're currently experiencing when using the RTE flow. Then the suggested solution. Why is it good? What is the basic components of this solution? And finally, I'll show what is required from the app that will use this new API. Okay, so about the RTE flow. It was designed around 4 years ago. It supports around 57 different items and around 70 different actions, which is quite a lot. It's used by all application that requires any flow routing, basically all application. I don't think there is one application that really doesn't use it. At least one action and at least one item in the RTE flow. It is supported by all vendors. Each vendor supports some subset. I don't think there is one vendor that supports all actions or all items. Each vendor supports some subset, but there is a common subset that all vendors do support. It is sequential, basically, this API. This API means that when called, it's blocking the rest of the application, the rest of the use case, and then the rest of the application, and then continues. And the assumption is when you're inserting a flow, the flow is inserted as soon as you're returning from the calling function. Each flow is a standalone flow because basically when you're inserting a flow, there is no notification to the PMD or the hardware if this is the first flow of a kind, or if it's just one flow or 1 million flows are going to follow it. So each time it's just one flow. In addition to that, when it was designed, it was kept in the OVS in mind. I will see that in the next slide what it means, but it basically means that we're considering the RTE flow as a control path and not data path with all assumption. Until now, for example, you were not allowed to call it from different threads. It was only control. We'll also see that later on in this presentation. So when we are looking closely, we can see number of usage application. Our applications are using the API. First, we'll see the OVS example. Basically, in the OVS example, we have a number of data workers that are running on different cores. Each data worker basically acquires the packets that runs some application logic, and then it decides if it wants to offload the flow. It sends it to a message queue, and then forward or drop the packet, whatever the logic is. So we have the data workers that are basically part of the data path, and then we have at least one control worker which runs on a dedicated core, basically pulls the message queue, runs some application logic, and if it's decided to offload the flow, then it calls the RTE flow. So basically, in this case, as we can see, the RTE flow is really not part of the data path. It's part of the control path. the blocking here is not affecting the data worker. It's affecting the insertion rate and everything, but it doesn't affect the data worker itself. This is one use case, and this one designed the RTE flow, this was what was in mind. As more and more applications started using the RTE flow, we got different kind of application. For example, a 5G application, security application. Their mode of operation is a bit different. They basically have only data workers. They, just like in the OVS case, they're acquiring the packets, they have application logic, they decide if the flow should be offloaded. But if it should be offloaded, they're offloading it right from the data path. So in these cases, we can see if it is a blocking API, if it's a slow API or anything like this, it does affect the performance, the total performance of the PPS or all the packets that can be inserted or offloaded at all, or not just offloaded, handled by the application itself. So after seeing both of those applications, we can see that the limitations of the RTE flow is, first of all, it's synced. It's not designed for data paths at all because it's synced. It has blocking calls. It requires locks. Currently, like last year, there was a patches introduced into the community that allows usage of calling to RTE flow from different cores, from different threads. But again, this introduces the locks. The locks are internal inside the RTE flow, but it still requires locks. The all logic, how to create the flow, how to analyze the flow, the allocation, the resource allocation required for the flow is done during the data pass, during flow creation. Each flow is a standalone, so the PMD/hardware cannot prepare and utilize resources better because it doesn't know what to expect. It doesn't know if the next flow is going to be inserted immediately or what resources he needs to allocate. So basically, each time a flow is inserted, the application locks. It requires firmware call or hardware call to the hardware. It requires allocation of resources, and all of that meaning that it's very limited on insertion rate possible. So this is the main draw of the RTE flow, of the current API of the RTE flow. So what is the advantages? Of course, there is a lot of advantages for the RTE flow. First of all, it's widely used. Like I said before, all applications are using it. All manufacturers are also implemented it in some variation, more or less. It already supports large number of acts and items. And it's very convenient for applications that requires only small flows, or only small number of flows, so that they don't need any fast insertion or anything like this. So there are a lot of advantages. So what is my motivation? What is the target that we are proposing? First of all, we don't want to replace the RTE flow. That's not the idea. The idea is to improve, to allow for high scale rules to be inserted faster. It's not a new way. It's not a new system. It's just an improvement to already system. And so basically, we want to allow the RTE flow with this item to work as part of the data path, to allow fast insertion. I'm writing here for high scale flows, but basically it's for anything. Even if you have small number of flows, it's still usable and still will get better results. We want to allow the RTE flow to be more robust and use more mindset about using multi-threaded, and basically achieve the insertion of removals of millions of flows per second. So this is the motivation that we have. Okay. Secondly, what are the assumptions? In order to create the best API, we need to have assumptions. So first of all, the assumption is that the application knows what it expects to, what what flows he is expecting to see, what action he expects to use. It knows around the number of flows he expects. He knows the number of counters. He knows there is a lot of information that the application knows before even starting or immediately after starting. It's not like each time he gets something, it's totally new. He knows what is expected to do. We also expect that application will be multi-threaded environment, which makes sense. We assume that most flows have some common structure. For example, there are types of flows, for example, that we have control flows, for example, DCAP, that we have very limited number of those kinds of flows. But there are also flows that have high scale, for example, connection tracking or anything that regarding 5 tuples. So basically, they can have millions of 5 tuple flows. All the flows are 5 tuples. It's just the difference of items, of the values specific in the items that we are trying to match. But from the structure, from the actions, from which item we are testing, they're exactly the same. We don't care, the application doesn't care about when the flow is getting inserted and if it's getting inserted. Like we saw in the OVS case, the applications offload the flow. Sometimes it will take after the packet processing. It really doesn't care because the application has its own software fallback. It utilizes everything. If it was offloaded very well, it saves the application work. But if it doesn't, it's also okay because the application assumes that it will get the traffic. So this is very critical. There are different kinds of flows, is meaning that there are sometimes flows that the application must have before, for example, DCAP or any control flow. So in this case, he will submit the flows and poll for completion and only then it. So it's also possible to add important flows that the application wants to guarantee that are in a specific order. But the main flows, the main capacities of flows, the large number, we don't care about the order. We even don't care if they're really inserted or when, but we don't want to slow down the packet acquisition process, the data pass. What is the suggested solution? First of all, we want it to be queue-based. The queue-based, it will also allow us to use multi-threaded, like we know in all DPDK-related data paths. They are queue-based. They are assuming that each queue can be only accessed from one core, so no locks at all. That's first of all. Second of all, we are assuming we are aiming for async operation. So basically, inserting the flow will not block the application until the flow is really inserted to the hardware. It's basically allows to continue. If the application wants, it can query if the flow is inserted or when it is inserted. But for normal flow, application workflow, it doesn't really mind that. Lockless. In this case, we again accept that the queues are lockless. We assume that we'll get to that in a moment. We don't want to have any locks, even for allocations of memory, allocation of other resources. So basically, we want everything to be as lockless as possible. Even though some flows are between queues, or at least inserted to be between a number of queues, we want it to be lockless. We want it to be optimized for insertion rate. This is a tricky line, and I have another slide about it. So let's keep it in mind for a second. And most importantly, not most importantly, it's very important, we want it to be able to connect to existing RTE flow API. When I'm saying that, it says 3 levels. First of all, we want to use the current RTE flow items and actions. We want that each action that will be added will be automatically supported by both the current API and the new API. And we want the ability to have the application use both APIs simultaneously. For example, for slow flow, for small number of flows, you can insert them using the old API, the current API, while for high rate traffic, it will be able to insert them using the new suggested API. So basically, it's not a new API, just in addition to the current API. Another key aspect of this API is that we'll split the logic of the API into two logic configuration, which means it's cross queue. It's not the function will not be based on a queue, and it assumes that this function will be called relatively small number of times, and in a most logically even before the really traffic begins. This configuration will allocate resources, will allocate memory counters, whatever. So when inserting the flow, there will not be need to any more allocation or anything else. Everything will be configured. So the configuration is, I wouldn't say once in a lifetime, but is relatively rare. And when it's called, may cause some hiccup to the system. But the data path, the insertion of rules, is as fast as possible. This is a very clear and key to understand that there is a pre-processing and the data path really of insertion that is very fast and should be as optimized as possible. When I say optimized for insertion, right, it can be a lot of things, but two critical things are stands in mind. First of all, in order to do that, we need to get ints from the applications. The application knows how many flows it wants to insert. It knows the format of the flows that it wants to insert. It knows what action it wants. So all of this information can be given to the PMD and to the hardware before really inserting the flows. So the PMD can allocate all needed resources, can even combine actions together in order to give the best performance according to the specific hardware. Everything this application gives, all this information is by definition an int to what it wants. Like currently at the RTE flow, since by definition it's really dependent on hardware, we assume that each manufacturer will have different usage to the ints, and not all ints will be available for all PMDs and will be used by all PMDs. But the idea is all the information the application can give us, let's take it. Some PMDs will be able to extract something, other will be extract more or less, depending. But the idea is to give as much as we can to the PMD, can pre-allocate and and optimize its path as best as it can. Another thing it's important to understand that the optimize for insertion rate is the state of mind of the developer. Currently, when there is a difference when a developer is coming to an issue that involves the data path, or it involves a control path. So in this case, he needs to understand that when he's coming to insert flows to the insert flow, this function is going to be called millions of times. So everything there should be optimized for speed. And this is a very key point from the developer point of view when it's coming to code. For example, I don't expect to see any validation during this stage, because the concept is it should be as fast as possible. It's really part of the flow itself, of the data path. Key structures and functions that is planning to hide. I will I see that there is some question. I will ask it in. I will address it in a moment. Okay. And I think for the questions, there was a question about slide 11. If the configuration works in different of processes. Currently, we're talking about one process and multi-threaded, but again, there is no limitation. The API itself supports everything, and the idea that the configuration is across threads and across processes, if possible, of course, if the hardware itself supports it. So the configuration is global, and then its rule is thread allocation. I hope that's answered the questions. So continuing on, we have the key structure and functions. Basically, we are introducing a few of them. I'll talk about only a few: table, actions, and configuration and queues. Tables. Basically, a table is something that groups flows with the same group ID, with the same priority, and with the same matching mask. So if I'm looking here, we see the group. This is already defined in DPDK. And currently in DPDK, for each flow, we defined which group it belongs to, what is the priority, what is the mask that we want to use, and what is the spec. So the idea here is that we'll create a new structure that is a table. It will have the priority and in which group. It will also have the mask. For example, in this case, we have the mask ETH with mask source MAC we want to match, and IPv4 with mask source and desk. This defines a table. And then based on that, the application can allocate all resources it needs. It will also tell him how many flows of that type are going to be inserted. So the PMD/hardware can prepare everything needed. And then the insertion of flow is just giving the parameter themselves only the specs. So as you can see, when I create the rule, I'm just saying, okay, this is the spec, source MAC, source IP, source destination, and to which table it belongs. So here we see that we use previous knowledge, we know about it, and we just analyze much faster the flow insertion. We don't need to recreate something. We don't need to search. We know what we're going to get. Just like we saw for the items, we have also the action. We have the basically the action template. In this case, we try to configure, the application tells us what is the types of actions that will be used for a flow. For example, the application can tell us that it uses the counter, it uses aging, using modify source MAC, and then jump. So all rules that using the same template will have all of those actions. The instance of each counter and the instance of each aging will be different. Also, probably the source MAC that we are going to set. But all of them will include everything. So this means that the PMD, even before the first rule, we can tell on how many, what is the memory consumption it needs. You can allocate, pre-allocate all the resources required. It can sometimes say, okay, I see that we have counters and aging for each flow. So maybe my hardware supported and I can do just aging because the counter is byproduct in this specific hardware. Maybe I can do anything. So basically the PMD can use some logic and understand how it's best for him to utilize this information. The specific value, for example, the specific counter that will give in the specific MAC to be written will be per each flow. Rule creation. This is the main idea. It's more conceptual, is that it's considered a data path. So everything in this function should work as fast as possible. There should be as little as a memory allocation, as little as resource allocation, no testing, whatever. It should be run as fast as it can. Secondly, it works on queue. Unlike now that the rule insertion, we basically assume that rule insertion will be inside the queues. So it automatically, it means it's multi-threaded. Not multi-threaded by definition, because each queue it will run on different thread. So this will give us the multi-thread. And basically just combined the table that we created before with the action template with the specific values of items and action that we want to use. Here we can see a simple flow of the application. In green, we can see what is basically needed. This is the configuration of the item of the application. We see that we call RTE flow configure, which defines the number of queues. We can find the number of resources required. And then we create the action templates and the item group, sorry, the item table, in order to be used later. And then if we look at the worker, basically what we can see is that just like previously, we have the RX burst, the acquisition, the analysis of packet. But let's assume now we want to create a flow. We're creating if the table and matcher are created. If not, we'll create the application may cause an hiccup in this case because those are not best optimized. So it's preferred to do it in the init stage, but it is possible to do it in this stage. And then we have the queue insert, which is highly optimized and assumes that everything was defined, and so it can work as fast as it can. And of course, it's asynchronous. So in order to get results and in order to advance the state machine of the hardware itself, at the end, the application needs to call for poll for completion. Sometimes it is not really wants the completion, but it can call for completion. So basic recap. The plan is to add new capabilities to the flow. We are not going to replace the current RTE flow. It's not the main purpose. It's just to introduce new capabilities to allow the RTE flow to support high insertion rate and to work inside data path applications. And it's to change the state of mind that we are now RTE flow is part of the data path and not just part of the control path. This is the most important things that I want to take from this presentation. As we can see, the next step is to submit it. I'm going to submit an RFC in the next few weeks. And this presentation, basically, I didn't show any API in purpose. They are already somewhere coded, and at least the idea of them are recorded. But the idea of this presentation is to introduce the concept of this API. So when coming to review it in the next few weeks, and if you have any other things, if you're thinking on other ways to improve or what is missing, so this is this call of action to say, here, we saw that we are missing something. We want to move it to the data path. Think about it. Hopefully in a few weeks, very short weeks, we'll have an RFC, review it, think about it, how can it be improved? This is the next steps, and this is the idea of this presentation, to make you to get you to think what can be done better, and that's it. Any questions, comments? Okay. Thank you very much.